video, we'll be learning how to solve work/power and energy problems for IB Physics SL. Now let's get into solving. Problem number 1. Consider a 0.5 kg book resting on a 1.5 meter tall shelf on the roof of a 100 meter tall building in a city 500 meters above sea level, which is 6,378 kilometers from the center of the Earth. Calculate the potential energy of the book relative to A, the floor, B, the ground, C, sea level, D, the center of the Earth. So first we have to remember our equation for potential energy, which is potential energy equals mgh. So now that we have this formula, we could solve for our first part. We know that the mass is 0.5 kg, g is 9.8, and the height is 1.5. So now we could plug those into our equation. 0.5 times 9.8 times 1.5, and if we multiply that, we get 7.4 joules. Part B. So find the potential energy relative to the ground. So same formula, EP equals mgh. We're calculating the potential energy relative to the ground, so the only variable that will change is the height, which would be 1.5 meters plus 100 meters, because that's the distance between the book and the ground. So we could substitute our values again. 0.5 times 9.8 times 101.5, and if we multiply that, we get approximately 5 times 10 to the power of 2 joules. Part C, we're finding the potential energy relative to the sea level, so the height would be 1.5 meters plus 100 meters plus 500 meters, which would be 601.5 meters. So we could again plug those in. 0.5 times 9.8 times 601.5, and we get 2900 joules approximately. Then for part D, we're measuring the potential energy relative to the center of the Earth. So the height would be 1.5 plus 100 plus 500 plus 6378000. So if we multiply all our numbers, we get about 31 million joules. Problem number 2. If the top of a playground slide is 2.7 meters above the ground and the bottom of a slide is 0.5 meters above the ground, how fast will the child be moving when he or she reaches the bottom of the slide? Assume friction is negligible. For this problem, we should start off by drawing an image of the situation, so we could draw a slide with a person on it. Something like this. Draw a person before and after. We know this distance is 0.5 meters and this distance is 2.7 meters. Once we have our picture, since we know energy is always conserved, we could say that energy before equals the energy after. And if we think to the starting position of the child, the kid is stationary but above the ground, which means that the kid only has potential energy. So for the energy before, we could just substitute that with the equation for potential energy. Right now we could write EP. And for the energy after, we know since the boy is going down the slide, some of that energy will be converted to kinetic energy. Also, we know that the kid ends up 0.5 meters above the ground, so the child will still have some potential energy. So with that being said, we could replace the energy after with the equation for kinetic energy plus the equation for potential energy. Now we could expand these formulas. So the equation for potential energy, mgh, kinetic energy is 1 over 2 mv squared, and potential energy again is mgh. And we see the constant m throughout here, and it's only being multiplied to other constants, so we could just substitute that out. Also, the problem doesn't tell us the mass of the person, so that's why we do that. So we could rewrite that gh equals 1 over 2 v squared plus gh. Now we could plug in our values. So 9.8 plus the starting, or times the starting height, 2.7, equals 1 over 2 times the velocity squared, which is what we're trying to find, plus 9.8 times 0.5, which is the height after. And if we just solve for v, we get v equals 6.6 meters per second. That's our answer for this problem. Problem number 3. A bike rider approaches a hill at a speed of 8.5 meters per second. The combined mass of the bike and the rider is 85 kilograms. If the biker stops pedaling at the bottom of the hill, how high up the hill will the rider go before coming to a rest? So same idea as the previous problem. Start by creating an image. We could draw a hill, like something like that, and then instead of just drawing a bike with a person, I'll just draw a box because that's easier. So again, energy is conserved. So E before equals E after. And what we're trying to find is how high up the person will go. So again, now let's think of what energy the biker has at the start and at the end. At the start, since the biker is moving at 8.5 meters per second, it has kinetic energy, and at the end of the problem the biker comes to rest, so the biker would only have potential energy. So for the energy before, we could replace that with EK, and for the energy after, we could replace that with EP. Now I could expand it. 1 over 2 mv squared equals mgh. Even though the problem gives us the mass of the biker, we could just eliminate that, because that's just an extra thing that we would have to do if we didn't eliminate it. So now we could plug in our numbers. 1 over 2 times 8.5 squared equals 9.8 times height, and if we just solve for h, we get 3.7 meters. Edit this out, by the way. God, I have to always do so much editing. It's getting a little annoying. On my daughter it is. But you know I have a daughter. Oh, sorry. Okay, wait, I'm starting back up. Problem number 4. At the top of the first hill, a roller coaster is 102 meters above the ground. It is motionless for a moment before plunging downwards. How fast should it be moving at the top of a loop-de-loop if the top is 42 meters above the ground? So we could start by drawing a picture. We could draw the first hill, and then, bro, I don't know how the picture looks like. Just edit all this out. Edit all this out, okay? Bro, this is gonna be the most editing I've ever done for a video, but it's fine. Edit this out. Keep editing. Keep editing. Keep editing. Bro, this is gonna have so many edits. On my daughter it is. Wait, I can't let them know I have a daughter. Frick. Lean it. Problem number 4. At the top of the first hill, a roller coaster is 102 meters above the ground. It is motionless for a moment before plunging downwards. How fast should it be moving at the top of the loop-de-loop if the top is 42 meters above the ground? So let's start by drawing the picture. We could draw the first hill and then draw a loop like that. Draw a box for the roller coaster before and after. So again, E before equals E after. And at the start, since the roller coaster is motionless, there's only potential energy. And after, since the roller coaster is moving and it's above the ground, it has potential energy and kinetic energy. So we could replace that in our formula. So EP equals EK plus EP. And then expand it. MGH equals 1 over 2 MV squared plus MGH. Again, we could cancel out M. And then we could plug in our values. 9.8 times 102, because that's the height of the starting position, equals 1 over 2 times V squared plus 9.8 times 42. If we solve for V, we'll get 34 meters per second. Problem number 5. A 3.2 kilogram mass resting on a frictionless surface is attached to one end of a spring whose constant is 29 Newton meters and whose other end is attached to the wall. The mass is then pulled 26 centimeters away from the equilibrium position and released. How fast will the mass be moving when it reaches a point 15 centimeters from its equilibrium position? First, we could draw our picture with a block with a spring attached to it. The first picture will represent the equilibrium position. So, spring with a block, that's our equilibrium position. And this is the before picture, when the spring is stretched out. And this is the after picture, where it's coming back. Something like that. Even though this is a spring problem, energy is still conserved. So E before equals E after. Before, when the string is stretched out, it only has spring potential energy, so we could say EP comma spring. Then after, since it's still moving, it would have kinetic energy, but since it's not at its equilibrium state, it would still have spring potential energy. So the equation for spring potential energy is 1 over 2 kx squared, kinetic energy 1 over 2 mv squared plus 1 over 2 kx squared. Here we could cancel out the 1 over 2's, and then our constant is 29 times 0.26 squared. Our mass is 3.2 times the velocity squared plus 29 times 0.15 squared. If we solve that, we get V equals 0.64 meters per second. And through solving all these problems, we could see there's a pattern where you have to first just draw your picture and then recognize which forces are before and which forces are after in the problem. Thank you.